Thank you for the invitation. I have learned some things in the last hour that I didn't know before, but I don't think I have to retract anything I said here, but we have a little more data. So this is the most amazing discovery in astronomy in a very long time, and so I'm going to ask questions and constrain some answers, probably not give answers. So here are the basic facts we have to explain. Durations from are as observed, in some cases, upper limits of a millisecond without actually being directly measured, up to about 15 milliseconds. The lower bound, again, is not a measurement. It's an experimental upper limit because of the intrinsic time resolution of the system. The longer durations, as we were told a little while ago, have a frequency dependence as roughly as the -4th power, always consistent with the -4th power. And that indicates broadening by multipath scattering, meaning that, again, the measured widths are only upper limits on the intrinsic widths. Most of them are at high latitude, which, of course, rules out population like galactic pulsars. Dispersion measure, and, well, you have the range. You heard that a little earlier. I'm in general going to tacitly subtract the interstellar contribution and exclude FRBs that are at less than 20 degrees because below that latitude, the galactic contribution is both substantial and very uncertain. So the remaining dispersion measure is greater than that of just about any galactic pulsar except a few very exactly in the plane. And if you attribute, using standard cosmology, the dispersion to the intergalactic medium, that tells you the redshifts. And when everyone says cosmological distances for these, that's what we're talking about. We're not talking about Z of 6 as in gamma ray bursts. They are the fluences, as observed by Parkes, 10 times less for the Arecibo one. Now, that's 10 to the 40 ergs or 10 to the 43 ergs per second. If you compare that with other astronomical transients like gamma ray bursts, this is 10 orders of magnitude less than gamma ray bursts and several less than supernovae. So we hear a lot of talk about finding them at other wavelengths, but radio astronomy is enormously more sensitive, partly because of the large collecting area and partly because you're not subject to quantum noise, which you are even in visible light. And so if they're going to be detected at any other frequency range, the energy is going to be overwhelmingly by several orders of magnitude in the other frequency range, which is a sort of way of hinting that I'm pessimistic about such detections. We've learned that there have been more polarizations, but the interesting thing here is there's a measured rotation measure. And retranslating previous estimates, there are about 1 million per sky per year. A few other things I didn't list when I wrote this. One repeats, that's important. It rules out all catastrophic collapse events, some neutron star turning into a black hole or something like that. And there are no obvious identifications. It's not like the Crab pulsar, which bingo, hey, there's the Crab optical thing pulsing at precisely the same rate. So those are the basic facts. So questions we want to ask are, where are they and what are they? So when we ask where are they, well, first thing is to establish a distance scale. For gamma ray bursts, that took more than 2 decades, although if we'd only listened to Yusuf at the beginning, we would have known they were cosmological distances or taken that as a compelling case, but people were frightened of the implied energy. And then we would like to know something about their environment, because to do that, that's necessary or at least helpful to determine what the actual sources are. Okay, so the first question is, where is the dispersion? As you were told this, I think, twice in the last 2 talks, so this is the 3rd time. The usual delta T goes as 1 over nu squared is, in fact, the first term in a power series expansion in the ratio of the plasma frequency squared to the observational frequency squared, and usually you only have to take that first term. The fact that it agrees exactly to error of measurement, which is a few thousandths, there varies a bit from burst to burst, but always consistent, gives you a constraint on the magnitude of the next term, and you can turn that into a constraint on the density of the matter that's providing most of the dispersion, and there it is. Combine that with the observed dispersion measure in the cloud that provides the dispersion has to be at least a couple of astronomical units. Probably excluding stars and coronae, not necessarily excluding winds from some great big supergiant. As you were also told, there's a constraint on plasma density. I would point out that that depends on the assumed temperature. So these are scaled to 8,000 degrees and 1,000 parsec cubic centimeters. 8,000 degrees is typical for an ionized interstellar cloud H2 region and so on. But if you go to something like a stellar corona, the temperature could be very much higher, and that relaxes this constraint, I mean, by orders of magnitude. Okay, so naturally one thinks of violent events, one thinks of the products of supernovae, and so first question you'd ask, could the dispersion be in an expanding supernova shell? Well, when supernova shells expand, they thin out, the column density goes down as 1 over r squared or 1 over t squared because they move in essentially unaccelerated motion. And so such a model makes a prediction for the shape of the distribution of dispersion measures. And I've given you here some numbers scaled to a 1 solar mass shell. And you can see that the shape, the theoretical shape with an eyeball fitted multiplicative factor is that sort of dish-shaped smooth curve. You can see the data from 17 high latitude bursts, so I'm not quite up to date, but these are the ones I had available. And you can see the shape is completely wrong. Now, you could imagine a cutoff, the cutoff times there, suppose the thing dies after, say, 30 years, that'll impose a cutoff at that vertical line labeled 30 years if the shell's expanding at 3,000 kilometers a second. That's pretty slow for supernovae. I was trying to be generous. If it's 10,000 kilometers a second, then that's a 10-year cutoff. So the point is to avoid that divergence at small dispersion measures. If it's a supernova shell, it's got to be, the intrinsic source has to shut off not long after the event created it. That isn't impossible, but it's a constraint on theorists. We also look at the distribution of dispersion measures. This is a cumulative distribution in the opposite sense. These are the ones that are that are less than the various numbers indicated down there. Galactic is excluded, and I've ignored the low latitude events because I don't think you can take out the galactic accurately. Again, an eyeball fit to a very simple sort of pseudo-cosmological model. It isn't really cosmology. Basically what you're seeing there, they're a deficiency, or I should say a few, it's not a deficiency, at small dispersion measure, and that's entirely consistent with three-dimensional Newtonian space. The volume goes as r cubed, which means it goes as dispersion measure cubed for just redshifts that are less than 0.7 or 1 or something. That's a pretty good approximation. Then you have to allow for the fact that in the more distant universe, the gas is denser, and that's actually folded into that smooth curve. So it fits very nicely. It tells you we're in a homogeneous three-dimensional quasi-Newtonian space. You notice there's also a deficiency at a very large dispersion measure, and there are very plausible explanations for not seeing those. One is simply that high dispersion makes them harder to detect because it spreads out the pulse within a frequency resolution bin of the analyzing instrument. They also are at greater luminosity distance, so they're going to be fainter. And finally, the energy is redshifted. But the flux, we're measuring fluence here, so it's only 1 power 1 plus z, not 2 as it would be for intensity. Okay, so now let's do the next standard thing in this sort of business. We look at the log n, log s, number versus fluence. Now, you get the same, s is fluence, s is flux. All that matters is the Lebesgue inverse square law, again, a cumulative distribution. And you, in Newtonian or quasi-Newtonian space, you expect a -3/2 power law. Again, you've got a straight line there with an eyeball fit. It fits quite nicely with 2 exceptions. There's a deficiency below 1 Jansky millisecond. Well, that's no surprise. That's basically the detection or confident detection threshold. Then there's the Lorimer burst, which sticks out there like a sore thumb at 150 Jansky milliseconds. And if you look at that, you say, well, where are all the ones at 10, 20, 30, 40, and 50? And there should be a lot. And Lorimer noticed this in his original 2007 paper, and the fact that it sticks out like a sore thumb is probably the reason why most theorists didn't pay much attention to the subject until Thornton reported 4 more in 2013. We were just worried that this was interference, although it occurs in only 1 beam of the 13 beams at Parkes, which is an argument against interference. If I were going to go crackpot, I would say, well, maybe we're sitting at some local density maximum of the fast radio burst source function. And I don't believe anything like that, but it would explain it. After all, we are at a maximum of the cosmic density. It's called our galaxy. But these things are not galactic. Okay. So what does this tell you? Well, we have 3 striking observations about the spatial distribution. The dispersion measure, which I've showed you in 2 graphs. What I call isotropy, I learned earlier today, is probably not isotropy, but the theorists hadn't told us the distribution of search time on the sky at that point, so I didn't know any better. And then we have the log n, log s relation. But when I say isotropy, what I'm really saying is, no, they don't look like pulsars. They're not all sitting there in the galactic plane or on the slice of the galactic plane towards the galactic center. So As I say, this looks like homogeneous distribution in local Euclidean space for dispersion measures up to the point where if the dispersion is intergalactic, cosmology starts making space significantly non-Euclidean, with one exception, the Larimer burst. This suggests a flat distribution of intrinsic strength. The extreme version might even be a delta function, but we know it cannot be, and I will show you that in a few more view graphs. So distances, either of these things are very close, less than the thickness of the galactic disk, less than about 100 parsecs, and it's hard to find a model that works that way to provide the dispersion measure, or they are further away than the scale of cosmic structure, at least something like 100 megaparsecs. Now, one other striking thing is that there are no striking identifications. We don't have a bunch of them on the coma cluster or anything like that. So if they are not very close, they're probably at least 100 megaparsecs away. And I said I guess I've already said this, that the absence of very high dispersion measures or very low fluence are, I believe, readily explained as observational selection effects. You can't see things that are too faint or too smeared. Okay, Misui came up with a very remarkable discovery recently, which you were told about in the previous talk, but here it is. And what this is ignoring factors of 1 plus z, which actually you can absorb them in a sort of a weighted electron density. This is the electron density weighted parallel component of magnetic field. And it's remarkably small. It's about 1/3 of a microgauss. Now, galactic interstellar medium fields are 3 to 10 microgauss, depending on whom you believe, probably very heterogeneous. And in any other dense cloud, not so dense that it's forbidden by our earlier considerations, you generally expect the denser the cloud, the larger the field, based on equipartition arguments or magnetic flux conservation arguments or your favorite argument. So this is a much lower field than you get even in the general interstellar medium, and I think fairly persuasively excludes dense clouds of any kind. Now, low-density matter, well, the intra-cluster medium, a cluster of galaxies, probably has fields this low, but it doesn't have a significant dispersion measure. So this points, I think, rather persuasively towards the intergalactic medium as a source of the dispersion measure, and hence you go directly from using standard cosmology to redshifts and distances, and even semi-quantitatively, only semi, because you typically have sort of a 10% correction for the local galactic, and you can speculate about something going on near source. But most of the dispersion is unlikely to be from a near source cloud, because any plausible dense near source cloud, and dense even means 1 electron per cubic centimeter, is likely to have a much larger magnetic field than this. Okay, so there's summarized the case for cosmological distances, and I have to assume Occam's razor, because you don't assume Occam's razor that all fast radio bursts from a single population with common properties except for the specific location in space, the specific fluence that came out. If you start violating this, well, then no hypothesis is testable, because any disagreement, someone will say, oh, but it's just a different class of object. Well, that sounds very brave and sensible, except, of course, we were very badly misled about gamma ray bursts for much of a decade when the first soft gamma repeater was called in the published papers and accepted by most people a gamma ray burst, and hey, there it was in the LMC. So Occam's razor isn't always right, but it's a good idea to start with it. Okay. So it means we can combine data from different fast radio bursts and attribute them to a common origin. Okay, so we exclude galactic unless very close, roughly isotropic. It indicates a homogeneous 3D distribution. The electron density is homogeneous locally and, of course, has the obvious cosmological dependence. The magnetic field in the dispersing region is low. And now, this absence of reported galactic fast radio bursts, and this can be used, if you have all the numbers, which I don't have, to set an independent lower bound on the distance in the following way. We have a size scale, and we know how many galaxies there are per cubic megaparsec. If that size scale is small, there are lots of bursts per galaxy, because we have a burst rate, which is about 1 million per year per sky, and we have a certain number of galaxies out to some distance. And if that were 1 million, which is not cosmological because they're about 100 billion, if that were 1 million, then we'd expect to have had one of these things in our galaxy. Well, as was pointed out, and I'll talk about it a little more, you can see them out of beam with any suitable radio observation. I'll have to mention what that is in a moment, if they're above the horizon. You can't see them below the horizon. In some cases, the numbers are favorable. You can even see the reflection from the moon if the moon's in the right place and so on. Okay, are there alternatives to cosmological distances? Well, the difficulty of providing a sufficient dispersion measure at sufficiently low density, the frequency distributions of dispersion measure influence. I guess I've told you most of this. If they were in the galactic disk, well, they're not in the galactic disk. And now here we have the event rate. Now, of course, the closer they are, the higher the event rate per galaxy. So you need to look for models that can produce lots of these things. And now that we've learned that they repeat, some of them repeat, one of them repeats, and of course by Occam's razor, we have to assume that they all can repeat, could repeat, or have the same properties as the one that repeats, even if they haven't repeated in our database. If they're close, they have to occur often, but of course they don't have to be so energetic. Okay, if they're extra-galactic, then the galactic counterpart, as I said, is detectable out of beam. So there's affluence scaled to both a galactic distance, like a soft gamma repeater, and a cosmological distance, 3 gigaparsecs. And so if you had so what I've got, D there is the actual assumed distance. So if they're all at 10 kiloparsecs, which we know we can't be, then they're all 1 Jansky millisecond. But if they're all at a few gigaparsecs, then if you pulled one into the galaxy, had a similar event in our galaxy, but 10 to the 11 Jansky milliseconds. Well, we know that in-beam radio telescope sensitivities, Parkes, for example, is about 1 Jansky millisecond. Out of beam, you're only down by about 60 decibels. Sounds like a lot, but not when you're fighting 110 decibels, 10 to the 11. And you don't use Airy functions to find this because it's not real telescopes are not ideal apertures. So, if the distances are greater than 10 megaparsecs, roughly, then a galactic counterpart would be observed when? One would be observed in any radio observation that's sensitive to dispersed transients, which means when you're looking for pulsars. But you got to be sure it's not rejected as interference, because it's going to come in all the beams of a multi-beam survey, like Parkes, with very similar fluxes or implied fluences, because it's backdoor interference. Sort of like a periton. Well, that's why one of the ways we knew from the beginning that peritons were some sort of local interference, and we've since learned they're the break room microwave oven. Although how it makes that sort of radiation is, I still find mysterious, but it is. So there is always a possibility, and you have to look at, and theorists can't do this, look into the signal processing algorithm to see if it was rejected as interference, because as we were told one talk ago, there was in fact a fortuitous pulsar observation, so therefore looking for dispersed transients at the same time as a great big soft gamma repeater. Okay, so independent lower bound on distances. This is sort of what I've told you, what I was telling you about a moment ago. There's the rate per galaxy. It's the rate of, R here is a rate. It's the rate of fast radio bursts divided by the number of galaxies close enough by assumption for the burst to be detected. And that, at the galactic rate would therefore, if you make the assumption that our galaxy is like a typical galaxy, whatever that means, would be expected to be this. Well, so if you have an upper bound on the galactic rate of 1 per year, and again, I don't know what the effective observing time is, but let's take that for a guess, then the lower bound on the distance is about 65 megaparsecs, and you get that rate. There's a factor of 3 whose root you take if you just turn that into the survey time, because you want a couple of sigma significance. So 45, call it about 50 megaparsecs. So the simple fact that no galactic FRBs are observed in other surveys that might be sensitive to them, that don't throw away things that come in all the beams, sets an entirely independent lower bound on the distance, and it's completely independent of theory or modeling. It does assume that our galaxy is a representative galaxy and that FRBs occur in galaxies. I don't know what that first sentence, what a representative galaxy is, but I assume somebody does, or at least in principle. Okay, where does the scattering occur? So we make a little plot here of the scattering width, or rather I should say the measured width, but anything above about a millisecond is probably scattering width, versus dispersion measure, and it's a scatter diagram. And that tells you the scattering is not intergalactic. There are other more theoretical arguments for that. Because if we're intergalactic, the more distant ones would have larger widths. We also know that at the latitudes, remember I'm only looking at things at 20 degrees latitude or more, at those latitudes, scattering in our galaxy is insufficient at these frequencies to get a multi-millisecond width. And that tells you that there's some special region that's not like our galaxy near the source, like some giant star formation region or something like that. Okay, so scattering must be in the source regions. In some sense, they must be special, not like the general interstellar medium that we have. Supernova remnants are certainly special, but they fail the test of distribution versus number of log n, versus dm. So Penn and Connor suggested the regions near a nucleus of a galaxy. We have this wonderful pulsar with a very much broadened pulse near a fraction of a parsec from the center of our galaxy. And, well, if you put in those distances, you need an electron density of about 10 to the 4, very roughly, but that's consistent with our other bounds on electron density. So that could be explain the pulse broadening, but it's not obvious how that will make how a gas density like that will make something make a fast radio burst. It's not significant for accretion, for example. It's not going to short out a pulsar magnetosphere. It's a really, really high vacuum by any standard except propagating a radio signal at a gigahertz over many parsecs. On the other hand, there is this curious fact that the theorists who study these things predict quite a number of pulsars near our galactic nucleus, and only one has been observed. Okay, so that's sort of a where are they, and obviously I'm strongly leaning toward the cosmological distances using standard cosmology and attributing almost all of the dispersion to the intergalactic medium. Well, the fact that they repeat, we actually have two. We had one that has two subpulses that are a couple of milliseconds apart, and you compare those couple of milliseconds to the collapse, to the catastrophic destruction time of anything like a neutron star, that's tens of microseconds. That's a repetition for those purposes. So, and then of course we have as we heard in length in the previous talk, one that's produced some dozen plus repetitions. So that implies they're not a catastrophic event. They're not a stellar merger. They're not a stellar collapse. Neutron star isn't being swallowed by a black hole. It's not a supernova. It's not a gamma ray burst, which is some mixture of these things. Although it's possible that whatever makes fast radio bursts, in fact, I think very likely, is produced by such an event. Like if we talk about a magnetic neutron star, it's produced by a supernova and may also produce a gamma ray burst in its formation, but it's not that catastrophic event that produces the FRB, it's a subsequent history of whatever it made. So I'm going to talk about two known classes of very brief repeating events, soft gamma repeaters, which we've heard evidence it's not, but let's see where you might go with that, because it's not totally, they're loopholes, like the data processing, or a giant pulse from a pulsar. And we can set some bounds on these things. I would point out, because it's not generally appreciated, I think even by many gamma ray burst people, that the shortest time structure in a gamma ray burst is about 30 milliseconds. It's even substructure, and much less pulse length. And of course, FRBs we know have 1 millisecond time structure as an upper bound. Okay, first let me ask you FRB standard candles, which might affect us, and I'm going to argue here they are not. Here we have a distribution of dispersion of fluence versus dispersion measure, and for the high latitude events, and that is a scatter diagram. You see the Lorimer burst up at the top. The curved curves are for standard candles of various strengths, and of course you have a whole family of those things. And it's not. This is a scatter diagram. There's sort of a hole in the lower right, and the hole in the lower right is probably that it's hard to detect weak ones with high dispersion for good instrumental reasons we've been told about. So let's think about soft gamma repeaters. There's some striking similarities. First of all, is the duty factor, which for fast radio burst, I said an upper limit of 10 to the minus 8. That was before the repeater. The repeater is sort of rough, the order of magnitude roughly in that range. It's a millisecond per day. Well, sometimes it's tens of seconds, but that's only a small fraction of the time. So it's a very small duty factor. Soft gamma repeater is about 10 to the minus 10. So that's certainly a striking similarity. And remember, even if you're attributing fast radio bursts to soft gamma repeaters, the soft gamma repeaters we know about are a population selected for being close to us, because X-ray detectors aren't that sensitive, or gamma ray detectors. And so they may not be representative of much rarer but much more energetic soft gamma repeater-like events. So don't expect a close one-to-one correspondence. Time scale. What soft gamma repeater people often forget is that for 2 of the 3 giant outbursts, the rise times are less than a few hundred microseconds, which is entirely consistent with fast radio bursts. And they also repeat in a funny clustered way in time, which we saw. However, well, you were told about that last sentence. At our best chance to find it, we didn't find it. So let me just try to do this in half a minute. So if you have a soft gamma, this is basically what people talk about as a magnetar. You have currents flowing through the magnetosphere, not just through the dense matter, and that requires an electrostatic potential. You because the currents have to be quasi-neutral. The electrons are Lorentz factors, which might be several tens or 100, and there's some plasma physics that there isn't time to go into, suggesting how, as it starts to pinch, you could suddenly get a large energy release in the magnetosphere. It doesn't do any good to release energy deep inside the star, because then it just comes out as soft X-rays. Predictions. Well, one prediction, I'll just go to the last one, is that the repetitions should be phased at the rotation rate. That's a wild guess, 1 to 100 seconds. No evidence for that in the repeating FRB. What about giant pulsar pulses? Well, by definition, in a pulsar, the power is limited by the spin-down power. There it is. I've scaled the angular frequency and the magnetic field. The fact that the spin-down time is at least 3 years, because that's how long the repeater observed, gets you a bound. And so you have an upper limit of how long these things can last of probably a couple of 100 years. Now, if the energy and pulse length I put in there are for the brightest FRB that's been observed, for others it could be a couple of orders of magnitude more tolerant. And what are the predictions? Well, the most striking prediction is that such a thing might be a millisecond pulsar. Steady millisecond pulsar under this, just like soft gamma repeaters are also now in X-rays known as anomalous X-ray pulsars. And the nice thing about looking for that is that you're coherently adding flux. And you have a millisecond pulsar period of several milliseconds. If you integrate over hours, you can coherently add lots and lots of pulses.
So I'm trying to understand the emission mechanism, in particular in the context of what Sarah told us on the constraints on the spectral index, and then what Vicki said about the much more wildly varying spectral indices and the repeating bursts. And do you have any comments on the emission mechanism?
Well, no, I don't think this is going to tell you much about the emission reason, because the pulse-to-pulse variation in the repeater is very plausibly attributed to scintillation. And so my guess is this is all tangled up in scintillation, and you learn something about scintillation on the path length, but nothing about the source.
Just a comment about the suggestion that Shri made before, and it has to do with the beaming angle. So you did not have much on that, but the issue is if one makes the Lorentz factor very high and the beaming angle very small, then taking into account, for example, peculiar velocity of cosmological sources, the beam will sweep by us perhaps once, but not more than that, because such a narrow beam will miss the Earth at cosmological distances. Wouldn't you say so?
Yes, oh, certainly. And so and in principle, of course, you can get a beam width as narrow as 1 over the Lorentz factor, although not necessarily. You can have a spray of very energetic particles going out very broadly. And so that relaxes the constraints on instantaneous power, which is what's determining the constraints on the giant pulsar pulse model, the instantaneous power. Because in that model, the thing has got to give up its spin-down power, whether it's radiating a fast radio burst or not. So if you beam it, those constraints are much relaxed. Yes?
Your comment about interstellar scintillation, I think refractive interstellar scintillation, the timescale for that could be responsible for the modulation in flux, so that the clustering is actually a propagation effect. But the changes in the spectra, I think the predictions, and I think Jim Cortez has done a lot of work on this, for decorrelation bandwidths are much, much smaller than this sort of observed decorrelation bandwidth that we see. So I don't see how that could be scintillation.
Well, of course, the refraction is strongly chromatic. But if it is true that you, in fact, average over the chromaticity because, as you said, you expect the characteristic correlation bandwidth to be very narrow compared to the observational bandwidth, well, then the question is, and it's not, I don't know the answer, it's the question, does it, in fact, average over as if they were independent random variables in each sub-frequency bin, which, of course, is very narrow, perhaps as narrow as kilohertz, or can there also be lower frequency and refractive scintillation, which is also chromatic, of course, could contribute to that. And we see these big, giant, whatever they're called, events in pulsars, which are believed to be refractive. Extreme scattering events, yeah, thank you. So the answer is I don't understand it well enough to give you an intelligent answer. Sorry.
All right, thank you. Let's thank all of our speakers.